So really nice to have you all here. Let's check if it is recording. Yes, it is. And our camera is on, so we go to lecture 9. Everyone ready for lecture 9? And what's the mood? Yes. Yeah. Can I tell a story?
Yes.
Quite a nice one. I just went through the details again because each time I remember the story I laugh. So there is this metric in general relativity, G mu nu. It's written in a kind of interesting way, and actually there was a conference on it in North Carolina, and Richard Feynman, who has ever heard of Richard Feynman, a great physicist, Nobel laureate, American physicist, and did a lot in quantum mechanics. So there is this symbol. So G mu nu. Let's see. I can just. Okay. So let me do. There's this symbol. Sometimes it is this. It's called the metric relativity. So he went for a conference in North Carolina, and he arrived one day late. And he went to the airport to get a taxi. The dispatcher said, "Where are you going?" He said he was going for a physics conference in the University of North Carolina. Which of them? Feynman had no idea, because there are 3. State University of North Carolina, Chapel Hill, and all that. So Feynman then figured out, said, okay, that conference started yesterday. And you must have seen a bunch of guys looking just strange and talking strange words like G mu nu, G mu nu, G upper mu nu, G lower mu nu. The dispatcher said, I know it's Chapel Hill. And he picked the taxi. It was exactly at Chapel Hill. Same thing now. I heard you guys talking eigenvalue, eigenfunction, eigenstate, yeah? All this eigen. Imagine if somebody were listening to you. This bunch of people. What's eigen? Yeah, but that introduces today's class. It's about the language, the theoretical framework of quantum mechanics. So, quantum mechanics, we are going into operator methods, operator algebra, and later on, Dirac nomenclature. We will use Dirac symbols, and it will almost sound like G mu nu when you are speaking. Yeah, and people could use it to know who you are and what you're and where you are, maybe. So, how about this symbol here? Quickly. What state is the cat?
Alive.
What state is this?
Dead.
I prefer sleep. Thank you so much. I don't want to talk about it's asleep. Okay. So now, the state of the cat. What is it now? The full state of the cat.
Yes.
Yes.
Yeah.
It's in a superposition.
That's the word. You got it. It's a superposition of alive. No. The superposition of happy, asleep. And this is okay until we say, let's measure, let's find out, right? Let's set up a measurement. And if we find that the cat is, dead, then you caused it, right? Your measurement killed the cat. Because until then, you all said it was a superposition, right? Oh no, we are into fun times. And if it is alive, I caused it because I measured it, right? Okay. So it's a superposition. It leads to lots of things to think about, but the interesting thing is that experiments come out with results that our theory predicts the statistical interpretation. That this superposition of this state, if we take the square integral of it, we get the probability of finding these results. Experiments prove it. But we want a clean, clear language. Very specific, can even sound strange, like G mu nu, but when we get used to it, it makes things easy. It is to communicate knowledge about reality at this atomic and electronic state. Okay? So today, we'll do some work on the board, but before then, to connect the words, to connect the new terminologies, the new symbols, I would like to use part of what we did already. I would like to use my quantum dot system that I solved with my graduate student using approximation, infinite square well, and we use that system to speak about these words: eigenvalue, eigenfunction, operator, and things like that briefly. Then we work on the board and we answer some questions and then go into details as far as we can. Is that okay? We've got a plan. And so, quiz. Anyone ready? Can pick it up. Okay, 1 more minute. Thank you. Thank you. Right, everyone submitted. Thank you. All right, so let's solve it. Yeah. So let's see. So wave functions live in Hilbert space. What is Hilbert space? So complete inner product space. Yeah. Complete inner product for the mathematician. Product space. And for the physicist, space of square integrable functions. Yeah, square integrable functions. So, all square integrable functions are part of the complete inner product space. It just means that we can do this and get a solution. Otherwise, the wave function is not normalizable. That's the square integrability. Nothing terrible. Yes, the x. And if you want more fancy words, quadratically integrable functions. Quadratic. Yeah, quadratic in the wave function. And why? So that the statistical interpretation can yield what? Our probability. Why? Because probability, the square of the amplitude is related to the energy of the system, to the intensity of the system, something we already know classically. Yeah. And so it's expected that the wave function should yield that. Observables are represented by Hermitian operators. So we are going to give some of their properties. Hermitian operators. What else? Eigenfunctions. Which operator has no eigenfunction in Hilbert space for any complete value of it? Which operator is that? Anybody?
Continuous.
Sorry?
Continuous.
The what?
The continuous spectra, so like a free particle.
That's an example, but the operator itself is called what? That's a result that makes it not have a particular wave function. The wave function is not normalizable, so we're looking for the operator which has no eigenfunction. There is a function, but that function turns out not to be its eigenfunction because you cannot get a measurement, a real value out of it. So you have the idea. This is what you're talking about. Is that okay? This operator, which is the same thing as, is that okay?
Is that the momentum operator?
Yes, it's a momentum operator. It turns out that it's very important, but it has no eigenfunction in Hilbert space for any complex value of it. But we can do something. What can we do? We can restrict ourselves to eigenfunctions with the real eigenvalues. And what is that restriction? How did we do it? Instead of taking all the wave functions like Grace mentioned, those wave functions that are not normalizable, those are its proper wave functions, right? E to the IPX, E to the IKX. Okay? What do we do with those wave functions? We take them and make a linear superposition of them. In other words, that assembly allows us to have what? Gaussian wave packet. Yeah, from so many of them, we make a wave packet of it, which allows normalization. Yeah, so generalized statistical interpretation. If you measure an observable x on a particle in the state psi of x, 2, you are certain to get what? Just the word. Excellent. Everyone got that one. That is good. Well done. Eigenvalue. So, as I said, without much ado, any question, please? As I said, without much ado, we're going to try to use these words and expression in a system we've already looked at. The infinite square well. And to make it not boring, I'm going to use the infinite square well that is a bit slightly more complicated but practical, something I actually used in a work that is actually published. So let's do that. So again, we're doing operator methods. We're doing this formalism of quantum mechanics, and I want to show some of the formalism using real systems I have worked on. So last lecture, lecture 8, part of it included the infinite square well, and that looked artificial. There was also the square well that is not infinite, right? And a combination of that can actually solve real stuff. So let's get lecture 8. And where is lecture 8, please? All right, there we go. Yes. So just to flip it so that you kind of get back to where we were and see that that's where we were. So do you remember this exercise? That's where we stopped, right? That's a square well, a finite square well. We answered that question. It has discrete eigenvalues around here. But when the energy is higher up there, there are no discrete eigenvalues. Notice that I'm beginning to use the words. There are no discrete eigenvalues of the wave function because the energy here is continuous. And the wave number is also continuous up there. This is a combination. Let me keep doing that with real applications. So after we we did that class exercise, this slide tells you that indeed real quantum wells exist and can be made. Quantum dots. Who's ever heard of quantum dots? Yeah. What do you think they could be used for currently? Or what are they approximately? Approximately, they are artificial atoms. We can create them using semiconductors, and that should already tell you that perhaps they may be good for energy. Yeah. They may help improve the efficiency of solar. Yeah. Quantum yield could be increased using quantum dot. There are so many promising applications even in biomedicine. I am trying to use them as radiosensitizers to improve outcomes of radiotherapy in the case of brain cancers that are resistant to radiotherapy. Okay? I don't want to add that I'm getting promising results, but I am. We are. So, in reality, so let's get back to this. And we can clear that. Look at that. Electron micrograph of a quantum barrier formed by growing a thin, layer of aluminum arsenide between regions of gallium arsenide with atomic precision. We can do that. And this sort of mechanism will be the basis of, nano machines. Machines at the atomic level. Each atom is a part of the machine. Imagine that. Nanobots. Not just robots, but what? Nanobots. That's where we're heading to. Imagine having this teeny stuff. Parts are little artificial atoms able to get as nanobots to your blood vessel and do surgery and get back out. Yeah? Program. Oh, yeah, eyes are widening. Quantum mechanics can get us far. Yeah. So we can handle them, we can make them. They are now available even commercially, and then you use them, you study them, use the properties. So let me use the system of quantum dots in spherical coordinates to talk about operators, eigenvalues, eigenfunctions, eigenstates, and hopefully, by the time we get to eigenket and eigenbra, you will not be too surprised. So, this has been published. So it's a work I did with one of my graduate students. And just for your information, if you do research with me, it's a must that we must publish together. It's required. That's my internal requirement. So don't come if you're not ready to get results that lead to new knowledge in science. That's why I'm a professor. I could have gone to industry or something to make money. No, but I want to get new knowledge that people can then use and apply and make the world a better place, because I am already a beneficiary of other people's intellectual contributions. How about that? There's nothing wrong in being in industry anyway. So here we have particle in a box, which we've studied. Here we have quantum dot system. This is indeed what our quantum dot looks like. It has a core, cadmium, selenium, and then an outer part, zinc sulfide. That particular construct allows energy activation. Electrons can get from here, close here, but they will never jump away, except extraordinary energy is added and all that. So you can cause excitation here and then emission through here. But here, what the electron at the surface sees is like an infinite barrier, energy barrier. Yeah? Because all the air around it and every other thing around it is nothing like this conducting strip. Yeah, that gives it an energy gap. So, that's the construct. Using that, then, I and my graduate student, we applied the Hamiltonian operator on the state of the system psi. And our hope was to get what? What was our hope with a Hamiltonian energy operator? On the state psi, if psi is the eigenfunction of the energy operator Hamiltonian, then what should we get? Eigenvalue. In this case, the energy eigenvalues. Yes. That's how we'll calculate it, and that's what it should yield. So we are demonstrating what it means. So what is the Hamiltonian? The sum of what? What's the Hamiltonian? Let's make this snappy. You know this sum of what and what? I've said it before.
Kinetic and potential.
Kinetic and potential energy, and those are those expressions right there. So that's the kinetic energy of a particle, h bar squared, and then the gradient squared operator divided by 2m. We've used that. We can write that, this Laplacian or gradient squared, we can write that in spherical coordinates very clearly. And you will need to use it. We will use it a lot in angular momentum. It's easier done in spherical coordinates because it's about rotation. Okay? And remember, why did we use spherical coordinates? It's better. We're taking advantage of the symmetry of the problem. They are dots, they are spherical. So that works nicely. That's the blue, the Laplacian. That's our energy. And that's the guy we're looking for, the energy eigenvalues to our system. And let's see how we can express the potential, that artificial potential, solve it, and see if we get eigenvalues. And we will measure. After all, the quantum dots, they emit. If you activate with a certain amount of energy, they emit. Activate. Comes back down, emits light, that you know the wavelength. If you know the wavelength, then you know the energy of the excitation, and you will know whether your calculation is correct or not. That's exactly what we did. So, we solved for the infinite square well, and you know how we solved it? Same thing for various regions. Arrived at energy eigenvalues for our specified distance, thickness of that shell, okay? And applied it to the two species. Remember, it was like when we did the square well, the infinite square well, for example, we are thinking in terms of an electron in an atom. Okay? So we did it for the electron and for the hole. When electrons are there, they are electrons. When electrons are not there, they create what we call a hole, almost like positive charge. But let's not go too further. With these energy eigenvalues, we're interested in the band gap energy. We put the mass of the electron there because that's the m, the wave function for a particle. What particle in our case? Electron. So electron and hole. And we get emission. It's a quantum dot, it emits. If the light is red, what's the approximate wavelength of red? 600, 650. And this is a constant. H times C is a constant. So you know the energy immediately. In fact, the light was greenish. Greenish light. And our energy eigenvalues could then be checked. This is what calculation yielded. This is what measurement is showing. Do they match? They did match. And it is okay. So we got the matching condition, and it showed that indeed this band gap solved using the infinite square well and a small step for the barrier. That approximation works nicely. It gives us our energy of the band gap, which is related to this emission when you plug in the numbers there. Okay? So we got eigenvalues based on our measurement that matched very closely with the expected or calculated eigenvalues. That was good. That helped us characterize our system. So back to the main reason I did this. Operator, wave function, eigenvalue. So in that case, this wave function becomes the eigenfunction of this operator because it is yielding us eigenvalues. Why do eigenvalues matter? They are real. If it were position, then we will get a position. It will predict where things are going to be. So eigenvalues are real. Eigenvalues allow us to obtain observables when we use operators on the eigenfunctions, appropriate functions, okay? So let's then switch to the board to do the formal thing, the formal explanation of operator algebra and operators in general. Any question before we switch to the board, please? Any? Okay, good. So, who does it? Should we, sorry, let's decide as class, should we use the board or should we use the screen? Which one, please? Start with the screen. Okay. So let's do that. Number what, please?
24.
24 or 20, 24. Thank you. So 24. 24. Let's call this operator methods, yeah, and algebra. Operator methods, algebra. Okay. Since it is a matter of doing the formalism of quantum mechanics, so remember formalism. So we'll just be stating things in an axiomatic way. So first of all, what's an operator in general? What does it do? I'll just say operator. It's an instruction to carry out a step, a mathematical step. So an operator such as A with the hat to distinguish it from just ordinary symbols on a wave function will give us an eigenvalue and that wave function. So just to be very clear, this is the operator, and what is this called? So you name this. This is what?
Eigenfunction.
Eigenfunction. Eigenfunction. Just to be sure that we get the language, the G mu nu. And what is this? Eigenvalue. So what is all this eigen? What's the meaning of eigen there? You can use a mathematical explanation.
That it belongs.
It belongs to. That's correct. It belongs to. It's almost, it shows up very nicely in linear algebra. When we do matrices, yeah, the numbers that we get from working, take a matrix, multiply by another matrix. For instance, you take a vector, a column vector, multiply with what? Column and what? Row matrix. Then the numbers that you get, those are the eigenvalues. Does that make sense? So we'll do that in matrix format to see things happening. So formally, an operator, if it operates on the eigenfunction, will yield eigenvalue. There's an important thing about this eigenvalue. What must it be?
Real.
Real. Must be real number. Why? Why should it be real? It's a requirement. It is something we need. It's not something that is obvious in the theory. We put it into the theory because we need it. We want the results of measurements to be eigenvalues. Because when we measure, we will get real numbers. So we put it where we are constructing quantum mechanics, such that when we have an operator and we get the right wave function from solving the Schrödinger equation, the mathematical operation that yields the eigenvalue should correspond to an experiment in which we measure that aspect of the operator and get that aspect of what it yields for us out of the wave function. And to put that in simple terms, we do step 2, observables. Who wants to state it as an axiom from the book? To every observable. Observable is what we care about as the results of experiment. Quantum mechanics is to explain the results of experiment. So the observables are what we care about, what we measure. Yeah. Let me use abstract math term. For every observable, let me start with observable. For every observable such as A, there is an operator A hat such that, am I writing a different language? Anyone seen this symbol before? Very good, yeah, we have mathematicians here. So for every observable A, there is an operator A hat such that, yeah, that's the axiom, such that what happens if system is in a state psi, yeah, then the expectation value of that observable becomes just this. Make sense? Any question, please? This is axiomatic. It's an axiom. Quantum mechanics. For every observable, there is an operator. So let's give example. Give example of an observable, please. Quick one. Any observable?
Momentum.
Momentum? Oh, I'm sorry, Dirac. Okay, momentum. That's the spatial operator, right?
Oh.
But we can still use it. Let's assume that we will get the right state. Yeah. I'm glad we did the Gaussian wave packet of how to handle it. Okay. For every
How about just
let's do the momentum. It works with the restricted condition. For every observable such as momentum, there is an operator what? So, such as P, there is an operator such as P hat, such that if the system is in a state psi, then we can get the expectation value of the momentum, which you calculated. Do you remember? You did the expectation value of the momentum. You did the expectation value of position. You did expectation value of the energy. Yeah? Is it clear now? This is formal language for it, so nothing really too difficult. Okay, so observables. We now want to characterize these operators so that we know a lot about them even before we encounter all of them, and we can just answer questions easily. Can I wipe this, please? Okay, so let's get rid of the whole thing. So II is the linearity of these operators. Okay, linearity. Okay. So let's illustrate. If, okay, I'll just write it. A hat multiplied by a certain alpha psi plus beta psi, it should give us, this is the meaning of linearity, a alpha A hat psi plus beta A hat psi. And we can even make it a different thing. It doesn't have to be psi all the time. It can be even on another function. So let me make it look more general as it should be. Let's do phi there. And there will also be phi. Right here will be phi. What is this saying? Look at the operator. Look at the summation right there. It is stating that the operator can be distributive. Another nice, simple way to put it. You got it. I don't waste time when you get it. And just know that alpha can, in general, be complex. Yeah, same as beta. So alpha, beta, complex in general. Why do we do that? Because sometimes it is important to have complex values attached to our wave functions. Yeah? Why? The square integrability may require that sometimes. Yeah? And for generalization. Okay, so this works even in such cases. Let's go further. Apart from linearity, this one is so central. We are going to decide what we want to call it out of the options available in the literature. Which one do you prefer? Okay, another one. Which one? Hermitian. Okay. So, what does it mean for an operator to be Hermitian? Equals, you answer this from the reading. And we will illustrate it thoroughly. We will prove the hermicity of various operators explicitly. And it will be one of the questions in exam 1. And we will do it even with matrices as well. We'll do it in exam 1, do it in exam 2. Exam 2, there will be matrices. Yeah, because we need such Hermitian operators. For example, the Dirac spin and all that. So what does it mean for an operator such as this to be Hermitian? I asked you to revise. Yes, please.
That it's equal to its complex conjugate.
It's complex conjugate. That's one way to say it. That's correct. Yeah. But its complex conjugate is another, is a specific form of the self-adjoint. So it is correct here, correct? So, yes. Self-adjoint. It's more general. It reminds you of matrices. Yeah. Which is a complex conjugation, whatever was negative, positive, yeah, shift positions and all that. So that is it. It's so important that I leave it there. And we will prove the hermeticity of so many quantum mechanical operators. And quantum mechanical operators are constructed so that they are Hermitian. And the reason you will see is that making them Hermitian allows that thing we wanted, allows them to give us real eigenvalues. And when they are not Hermitian, we do something to them to make them Hermitian. Can I go further with this, with an example? For example, you could say momentum operator. Well, how are we going to make it a Hermitian? Well, it is related to this. And if you use just d dx, just that, it's not going to be Hermitian. It's not going to be its self-adjoint. And what you do then, hey, watch it. What do you do then? You make it Hermitian. By doing what? What can you do to make it Hermitian?
Partial.
Like Tucker?
You either add the negative I bar
Yes.
or I H bar.
You add this, which is the same as to make it Hermitian. So that it will become its self-adjoint. And that way you can get your real eigenvalues. Let's take the property further, the last one before we do class exercise. Can I wipe now, please? And just to make sure everyone is following, any question on that? Chemicity? Okay, so the last one. This is the last one will be, there will be an example too. Okay? The algebra. Algebra of operators. You can say operator algebra. So let's not talk too much. We say A plus B, these are operators, equals B plus A. Straightforward. But we note vehemently that A, operator A times operator B is not in general BA. In general. And this is profound. This is a big deal. To show that it is a big deal, watch it. Let's do operator P, operator X, and see what it gives us. Px. I can make it bigger in case you are reviewing this later. So operator Px. Let's test it on a function together. Psi. What does that mean? Are we together? So P is h bar over I, yeah, into x hat, yeah, psi. You can see that? So let's make this a little bit faster. So I'm going to just do P by itself. So d dx. So that's P. Do you agree? That's P. And now, to save a step, you and I work on the board. We got the instruction to take derivative with respect to position on x and psi. So, product rule, can we apply it? With x constant? Okay, we take derivative of x and keep psi constant. What do we get? Do you agree? Watch it. Take derivative of, so keep psi constant, take derivative, so 1. That plus. Next, x constant, right? And what do we get? Anybody?
Psi prime.
Sorry, psi prime, yes. Okay. So what does this give us? It is equal to h bar over I. Look at d dx right there for psi. Yeah? d dx for psi. That looks like P itself, right? You see? Okay. So we already had the d dx. We have actually done the instruction. So let me make it clearer. We've done the instruction together already. So I write it so that there is no confusion. We actually carried out that derivative, okay? Very good. I could see from your eyes that something isn't clear. So you are really helping me. So we put the h bar over I right there and put our psi over here and put plus. What do we get? There is h bar over I, and what else? If you like, there is that d psi dx. Notice that we are now getting this P hat x hat psi equals, watch it. Can we do I h bar here? What will that be? I h bar or negative I h bar?
Negative.
Very good. So negative I h bar psi plus, can we rewrite this as it shows itself to be? Look, there is x there, x hat, and this is just a constant. So what do we have? X hat and what? Look at it. This is a constant, so shift it there.
It's P.
Thank you, Tucker. So x hat
Times P hat.
times p hat. Everyone can see that? And what? There's something missing.
Psi.
Thank you. Wow. How about we cross out all the sides, because it's like doing nothing on both sides. What do we end up with? I'm waiting for you. What do we end up with? It's a big deal. See? P hat x hat equals negative I h bar. Oh. So we can rearrange and say x hat p hat. Can you see it there? X hat p hat. Yeah. Take this over there minus p hat x hat. I took this over there. Equals what? So equals what?
IH.
Can everybody see that? I hate you. That's probably one of the most important results in quantum mechanics. Because this is the origin of the uncertainty principle. This is the result of the non-commutation of the position operator with the momentum operator. They don't commute. And when operators do not commute, you can immediately state the uncertainty principle. And measurements show it to be correct. That's it there. And we can have this in a more concise expression. We can say the commutation of x and p, yeah, equals what? I h bar. So in future, when we have observables and pick out their operators, if their operators do not commute, then there will be the uncertainty. Heisenberg. Energy, time is another pair. Yeah. And good thing is that when operators commute, when operators do commute, then they share eigenfunctions, which is cool. And from solving one and getting the eigenvalues, you can easily infer the eigenvalues of the other. And we will do it. The energy operator commutes with the angular momentum operator. And by solving for the angular momentum operator, we immediately get, yeah, it's just sweet from there. So these abstract sounding formalism principles or axioms are actually helpful in getting us there in so many instances. Any question before we then try to answer? Question from, yes, Billy.
So if they commute, there will never be anything left.
Yes, very good. So good question. So in general, if, okay, I can write, so I just said AB do not commit. So what if they commit? That's Miller's question. If they commit, what's the symbol? If commute. It means AB minus BA equals 0. It means AB equals BA. But we just said that in general it is not true. And we showed it in the case of momentum and position operators. Is that okay? All right. So, any more? That was a very good question. Any other one, please? All right. So back to the slides where we do some exercises. Let me see, we're going straight into the exercise. I'll give you a little break and then we go straight into the exercise. Okay. How about you take 1 minute break and then we do, oh, it's almost time, but do we just finish it? 1 minute break is fine. Yeah.
Rob. Size. Yeah, I can do it on size.
Oh. Never mind. I'm stupid. So like they're supposed to be the
Yeah. How does this Where does this come in? It's abstract, so it's exactly not necessarily the context of like matrices. So an eigenvalue is the like result of an operator basically. Once you eigenvalues are like states of the operator. Because you have like the operator times psi equals an eigenvalue times psi. So the operator is like a function, and the eigenvalues are like the roots, like the values of the function.
It's like measured. So when you have the infinite square world, right? Your eigenvalues are your different energy states that you can have. So that's it's like n squared and all that stuff.
So E equals n squared blah blah. That's
Yeah.
an eigenvalue.
Yeah, all those different for every single value of n. Those are all separate eigenvalues.
And that's why the eigenvalues have to be real, because you have to measure.
Yeah, you're not gonna have an imaginary energy.
But all those energy levels are described by the Hamiltonian.
Correct.
Which is an operator. Gotcha.
Okay. Group work. Decide together. Work together.
Alright. Got it.
Discuss and ask questions.
Well, 1 and 2 are correct. We know 1 is right. So if you
What's
choose
that?
observable,
Based-
well, 2
Based
is
on my
I
limited
don't-
understanding of
I don't necessarily
we talked
they all
about
look right.
those on the
yeah. I think
feel like
it's
it's
just like I don't completely understand.
No, we just talked about
I
it.
know
Yeah.
3 is.
I know 2 is correct because it says that must be from my operator. It says that
Yeah.
it's observable and that means it's information.
Yeah.
So
And that
That's what I think.
well, so in order for 3 to be true, then Q has to be true.
I think in the book it says that
Says observable.
I think E is just the
What?
it's just bigger.
Oh yeah.
It's saying choose
That's
me.
what I said.
So 2 is
I
right.
know. It's just saying choose me.
Exactly.
Yeah. It is.
If it's
Yeah,
not.
It's 2 and 3.
Yeah.
I don't know.
Oh, I guess direct.
It's in
Because if the eigenvalue of Q is gonna be real,
I don't know which one
Q
they
is the operator.
Yeah, I think they're all true.
Yeah.
So the conjugate.
I think they prove each other.
3 is sort of almost a
There's 3.
So that's right.
Actually, that's
Q is an expectation value.
Finish your thought. Finish your thought.
So 1 is.
Okay, can we vote? Any groups sure? If it's so?
we're sure.
Oh, we're 100% positive.
And what is that?
Joe, you wanna tell him?
Gonna go with E. All of the above.
I'm positive that I think it's E.
Wow, I like that. So that group gets it right.
Yes. Yeah, we do.
We told them the
E, correct?
What the?
Good job. Many of you did. I listened to you and you got it. Yeah. So we have done 1 and 2 thoroughly on the board, right? A little bit indirectly, but not very clear because there is the Dirac notation which I've not yet introduced. So this means, since we're at it and you did so well, I can just show it right away. So this is called R. And this is called, don't ask me what happened to the C. That's exactly what Dirac said when he was asked what happened to the C. So that's due to Dirac. It's just another way of writing the state function. So as simple as that. And it allows us to think in terms of it's a faster and neat notation. It makes the complete inner product disintegration, square integrability. So it's just neat. You can do a lot faster with this. Yeah. Really nice. Since you are so attentive, how about I do this? So the expectation value then becomes, yeah. See how neat it is. Sort of, yeah, which is the same thing as this one that we know already. Integral. So
No, that's good.
yeah, that's because, so that's the Dirac notation. Just, and this becomes, instead of just eigenfunction, because it is the ket, we can call it eigenket. Eigenket, eigenbra. And we can work, it's very neat and concise. Cool. Yeah. So that then shows the hemicity of Q. Q is Hermitian, and that is why it can operate backwards on F, operate forward on G, backward on F to give us that, okay? Making it, and we will prove it, so don't worry. And also I have the proof on my slide. Let's do more fun stuff by letting you work as a group again on what we just did.